So my name is David. I'm a doctorate student at the ETH Zurich, and today I'm going to talk a little bit about interacting with maps on optical head-mounted displays. So more precisely, I'm going to talk about a little bit about how you can interact with maps in space for PCs and tablets, but more mainly with a focus on optical head-mounted displays. So imagine that you have an electrician who is actually working on an electrical plug and trying to fix that plug, and that electrician needs to look up the electrical schema. So the main interactions with this electrical schema, which can be considered as a map, is the electrician needs to pan it up, down, right, and left, as well as zoom into it and zoom out of it. So considering these space interactions and considering variables, we have the other way around. So considering today's variables, we have different devices. So more common devices are actually optical head-mounted displays or smartwatches, as well as more recently, or not there in the industry that much yet, sensors in the shoes or in clothing. However, we're going to focus today on the optical head-mounted displays. So what kind of interactions do we have available with optical head-mounted displays to basically be able to realize this mapping and panning on maps, zooming and panning, on maps? So on the one hand, we have haptic and other interaction methods. For haptic methods, there are some approaches which try to enhance this haptic interactions with adding belts. There are other interactions which suggest using sensors in the shoes to have feet interactions or even gesture interactions. Further interactions include hands-free solutions like using head motions, or even the really quite more common or older one, the voice recognition approaches. However, all of these have their downsides, of course. So additional weight, or that you need additional processing power for image processing approaches, as well as voice recognition, which is a little bit prone to problems when it comes to cluttered spaces or open spaces. Based on that, we chose, more recently even, there are some approaches which try to use eye tracking or gaze tracking to exploit interaction spaces, but that's quite new, and there haven't been that many papers on that yet. But that's an additional option for the future as well. So what did we do? So we want to combine our maps with optical head-mounted displays, and considering all the facts I mentioned earlier, we chose to focus on mainly focus on head-based interactions and haptic interactions. Both of these interactions are currently supported by almost all OHMDs in the market, and so we decided to use these. Now, we know we want to pan, we know we want to zoom, we know that we have chosen to use head-based and gesture-based interactions. Before we started off, we thought, well, what kind of interactions do we have? So we started analyzing the design space for interactions with exploiting these approaches. And we looked up this definition by McKenzie, saying that spatial relationship represents the mapping from movements of the controller in space onto movements of the display. So basically, moving your mouse and then the reflection of that movement on the cursor on the display. Or in other words, moving your mouse and the corresponding movement of your map. So if I would move my mouse along the x-axis, that would correspond to movements along the same axis on the display. If I would move my mouse forward and backward along as we call it in this case, the z-axis, then the mouse is actually moving up and down along a y-axis. Considering these mappings, and considering the mapping for zooming, which is like imagining that you're scrolling along the z-axis, which is also mapping onto the same axis, considering that zooming imagining that zooming is going into another layer of cascaded displays, then we see that two of these mappings, the x and the z mapping, are congruent. So basically, these mappings are what McKenzie tends to call intuitive relationships, whereas the relationship that I'm moving my hand forth and back and the cursor is going up and down is more a learned relationship. And he concludes that these kind of relationships are the ones to be preferred. Looking at touch inputs, we actually have similar mappings, whereas the x and y axis are congruent and the z axis is not, because no matter how I put my fingers diagonally or anyway, I still don't have a congruent mapping for that. So now we know about spatial mappings. We know that we want to zoom, we know we want to pan, we know everything. How does the design space look like for head-based and haptic interactions? So we did a thorough analysis, and we found that for the head-based interactions with regard to zooming, or generally for head-based interactions, we had one small challenge. We did a pilot study with several participants, and we found that they had some issues knowing where their head is in the space when interacting with our interfaces. So as a solution for that, we chose to basically visualize their current head position and visualize this interaction. So what you would have is basically two bars and a red dot. You didn't have the arrows and the zoom in, zoom out text, of course. And when the user basically moved their head up or down, the display was zooming in or out when the cursor was within that given area. We called this interaction ZH0, so it sounds more complicated than it actually is. So Z stands for, I come to that in a sec. So Z stands for zooming, H stands for using your head for zooming, and well, nod is nodding, right? So when I move my head down, I zoom in. Beneath the red bar, up, I zoom out. And when I'm within those two bars, I stay put. So looking at this interaction with nodding, we see that we have a mapping from rotation along the x-axis, as we call it, to zooming in and zooming out. So that's not a congruent mapping. Why? Well, obviously, you could think of the rotation, but you should think of it a little bit differently. So what I'm actually doing when I'm nodding, I'm looking up and down an artificial y-axis, at least how we call it, the y-axis. So I'm mapping from the y-axis onto the z-axis, and that's still not a congruent mapping. However, when it comes to panning, this looks a little bit different. In case of panning, we chose a similar approach because we still had the same issue, where we chose to basically have a square, and I saw a better animation than this one yesterday, but okay, sorry for this. Anyway, so when you move your head left or right of the bar, then you pan left, pan right. If you're in the center, you don't do anything up and down, you pan up and down. So in this case, looking at the mappings, at the spatial mappings, we see that rotation along the x-axis is mapping onto the y-axis. So I'm basically looking up and down the y-axis. So this is a congruent mapping. At the same time, shaking my head, so going left and right, is mapping onto the x-axis. And again, I'm just scanning left and right of an artificial x-axis. So again, we have a congruent mapping. Coming to the haptic inputs, the analysis showed more than these two approaches for zooming and panning. For zooming, it was that we found that we couldn't just go ahead and tap that glass, which we use in our study, because it led to displacements and errors, input errors. So we chose to just use a single x-axis in the dimension of a positive axis by pressing with 2 fingers to zoom in and pressing with 3 fingers to basically to zoom out again. Again, don't be scared of the annotation. It took us some time to get to a proper one. So this is zooming using touch inputs and then just pressing with 2 and 3 fingers. The next interaction was zooming. It was swiping up and down to zoom up, to zoom out, and to zoom in. So basically, I'm moving away from the map and towards the map. Zooming forth and back. So basically, going closer to the map and going away from the map. Or sorry, the other way around. Pulling the map towards me and pushing it away from me. And up, down, and left and right for panning. So looking at the mappings, we see that for zooming, the forth and back motion is of course congruent because we are moving our fingers along an artificial z-axis. Whereas for the panning, moving up and down moves the map up and down. That's congruent. However, moving forth and back just moves the map right and left. So we don't have a congruent mapping there. So we evaluated all these interaction methods with 31 participants. Each participant was asked to do 3 main tasks. First, there was a zooming task where participants had to zoom with each of the interaction methods. Of course, everything was counterbalanced. And for the second task, participants were asked to pan with the given methods. And for a third task, we chose to look a little bit at the combination of panning and zooming. So as dependent variables, we chose to evaluate effectiveness as the number of errors made with during the task. So when I'm basically zooming and I zoom too much in or out, that was counted as an error. And when I was panning and I moved away from a certain goal position, or I was moving towards it and then I started moving away, that was counted as an error as well. However, errors did not accumulate just to weigh out sensor inaccuracies. Furthermore, we evaluated efficiency simply as task completion time. We evaluated user experience with the user experience questionnaire and the perceived cognitive workload with the RANAS TLX. So with our assumption that congruent mappings between a control input and a display have a higher level of intuitiveness or should perform better with all the factors which we presented earlier, we set up the following hypotheses. First, we said, well, for the panning task, nodding and shaking your head, so basically scanning along the axis, this should outperform the other ones because it's basically fully congruent. And our second hypothesis was that for the zooming task, swiping forwards and backwards along the z-axis and basically moving the display along the same axis should outperform the others as well. And as a third hypothesis, we said that the combination of nodding and shaking, which is a congruent mapping, and pressing the button, withholding for zooming, should outperform the others as well, especially because the panning method was congruent. So hypothesis 1 could be confirmed because we found that it was actually significantly more effective than basically swiping up and down and forth and back because up and down was mapped up and down. However, forth and back was mapped left and right, and that was an issue. Our second hypothesis could be confirmed as well. So basically, zooming forth and back was more efficient, more effective, and really outperformed all the other approaches. And our third hypothesis could only be partially confirmed because it was significantly more effective, but there were no other significant differences otherwise. So in conclusion, we found that interaction methods with congruent spatial mappings actually could outperform others independent of the interaction modality. So no matter whether I'm using head movement or whether I'm using haptic inputs. And our head-based interaction method was actually significantly more effective for panning and for the combined tasks. So that actually supported this idea of us using some kind of visual feedback about when am I actually panning and zooming, and in that times when I'm within that box. Okay. Thank you for your attention. Questions?
It looks like you didn't try the nod shake for panning and forth and back for zooming in combination. Why did you not try that combination?
Actually, it's part of our future work to evaluate that. Somehow we didn't evaluate it. It's actually a really good question. That's definitely something we should do as well. It should actually outperform the other approach as well. Yeah.
Thank you.
Thank you.
Do we have any more questions from the audience? Okay, well, people are thinking, I'll ask a quick one for you. So I'm just wondering, I'm wondering how these panning methods might translate to some of the modern devices like HoloLens that are coming out where you can have spatial tracking and put something, say, I want to pin my application on the wall here while I'm maybe it's instructions to fix a machine that's over here. So how do you see this working if I want to move my head from this object to the application and then pan within the application?
So you would need some kind of multimodality for that, I would guess. So you cannot just move your head out of the box and say, nothing's going to happen. Yeah, something will happen. So you need to an additional trigger in some kind of way for that.
Great. Okay, let's thank our speaker.
Thank you.